Thank you for joining this presentation. My name is Christopher Almendares from Auburn University. Poultry processing focuses on converting products for human consumption. Although poultry are generally recognized as efficient converters of feed to food relative to other livestock species, increased production of poultry products leads to larger volumes of associated co-products. At times, organ meats have less economic value, especially if sold for rendering. Liver and heart may be undervalued co-products. These co-products are often redirected for other purposes than human consumption. Pet treats could utilize meat processing co-products as sources of nutrients. Chicken liver is considered as a co-product. According to Zion and others, approximately 3 million tons of liver are generated per year. Xiong and others determined that between 2 and 2.5% of the chicken live weight is liver. Chicken liver is a co-product of interest since it contains many nutrients, including protein, fat, minerals, and vitamins, such as vitamin A, B6, B12, and others. Liver has been historically hard to use because once it is ground, it tends to liquefy. Therefore, ground liver is more difficult to incorporate to product mixes. Chicken heart is also considered a co-product. According to Honekel, chicken heart makes up between 0.3 and 0.8% of chicken live weight. Link explained that chicken heart is considered a good source of protein and rich in iron. According to USDA, chicken heart boasts 26 grams of protein for every 100 gram serving. It is rich in riboflavin, zinc, selenium, and phosphorus. Algin is a combination of sodium alginate and encapsulated calcium lactate. Sodium alginate is a hydrocolloid, which are long-chain polymers used to improve the rheological and textural properties of products. Sodium alginate is used in meat processing due to its property of forming viscous dispersions and gels. For it to gel, it needs to be in contact with calcium or any other metal ion. These metal ions are necessary to help drive and stabilize the reactions and bonds. Algin inclusion could add stability and improve the quality of products. This improvement is achieved through the gelation process. Algin inclusion as a structure-forming component can restructure chicken liver and heart into pet treats. The type of hydrocolloid selected in the preparation of restructured products may affect the stability and quality characteristics of the final product. The objective of this experiment was to define the texture profile analysis of pet treats using mixtures of raw liver and heart from broiler processing with 2 inclusions of algin. The hypothesis was that the addition of algin in the chicken liver and heart mixtures will improve the textural characteristics of pet treats. To test this hypothesis, a completely randomized experiment design with a 3x2 factorial treatment arrangement was conducted. 3 different combinations of chicken liver and chicken heart meat and 2 inclusions of algin were utilized, thus generating 6 total treatments as shown in the chart. For the preparation of samples, chicken liver and heart were ground individually through the use of a commercial grinder feeder with a 4.8 millimeter grinder plate. In the image displayed on the top right, the liquid consistency of ground chicken liver is apparent. Ground chicken liver and chicken heart were mixed until uniform blend was formed into the following 3 proportions: 25% chicken liver, 75% chicken heart, 50% chicken liver and 50% chicken heart, and 75% chicken liver, 25% chicken heart. In addition, algin, which is considered a structure-forming component, was slowly added into each one of the 3 chicken liver and chicken heart mixtures at 2 dosages. The 1x algin inclusion represents the manufacturer recommended dosage, which consists of 0.85% of encapsulated calcium lactate for every 1% of sodium alginate. while the 0.5x algin is the half of the manufacturer recommended dosage. The different combinations were then stuffed into 69 millimeter diameter casings, refrigerated for 48 hours at 3 degrees Celsius, and sliced into 25 millimeter thick slices. The encapsulated calcium lactate used in this experiment releases calcium slowly over time, which may strengthen the protein matrix. This will provide better functionality for a wider variety of end product forms. The overall textural characteristics of slices of the raw chops were measured utilizing the Stable Microsystem Texture Analyzer, as shown in the image to the right. The TA 3-cylinder probe was used under the following conditions: a pre-test speed of 5 millimeters per second, a test speed of 1 millimeter per second for a total time of 5 seconds, a post-test speed of 1 millimeter per second, and each sample was compressed to 75% of their initial height. 10 replica slices per treatment were subjected to each textural analysis. In this test, hardness records the maximum force required to deform an object. Cohesiveness measures the structural integrity under compression. Adhesiveness determines the addition of the sample to the probe. Chewiness illustrates the energy required to masticate. Resilience captures a product's ability to regain its original form. Springiness logs the height recovered after compression. For statistical analysis, data were analyzed as a two-way ANOVA using the Glimix procedure of SAS. Chicken liver and chicken heart mixtures and algae inclusion served as fixed effects in the model statement. Treatments least square means were separated using the PDF option of SAS. Least square means were declared different when p-value was less than or equal to 0.05. Before discussing the results, it is important to mention that interactions were observed between chicken liver and chicken heart mixtures and algae inclusion for all the variables measured in this experiment. Please allow me a moment to orient you to this figure, as the following results will be presented in a similar manner. The y-axis shows the texture characteristic and its unit, in this case, hardness. The x-axis indicates the treatment combinations with the percentage of chicken liver and chicken heart in the orange and blue bars, and finally, the algae concentration below these. For the bars, color patterns will be utilized to illustrate the 6 different treatments. Different superscript above the bar indicate differences among least square means. The probability value and standard error of the means are displayed on the top right hand of the table. The combination of 25% chicken liver and 75% chicken heart at 1x algae inclusion recorded the greatest maximum force required to deform the sample than any other combination. Although, as shown in the graph, treatments with 1x algae concentration required more force to deform the sample. In relation to the other treatments, the combination of 50% chicken liver and 50% chicken heart at 0.5x algae inclusion adhered more to the probe, which is not the case presented in treatments under the 1x algae inclusion. The greatest height recovered after compression was measured when 50% chicken liver and 50% chicken heart was mixed with 0.5x algae inclusion, and the lowest recovery was recorded when 25% of chicken liver and 75% of chicken heart were combined with the 0.5x algae inclusion. The lowest potential for deformation before rupturing was measured when 75% chicken liver and 25% chicken heart were mixed with half of the recommended dosage. However, increasing concentrations of chicken liver in the combinations with inclusions of 1x algae had lower deformation, which was not observed in treatments containing only 0.5x algae. Increased ability for the product to regain its original form was observed for all samples containing 1x algin concentration, compared to those with only half of the recommended dosage. The highest ability to regain to its original form was observed when 25% chicken liver and 75% chicken heart were mixed at 1x algin inclusion. The energy required to masticate a sample increased with 1x algin inclusion when compared to those treatments receiving only half of the recommended rate, and was highest at 25% chicken liver, 75% chicken heart with 1x algin inclusion. As conclusions, due to the gelation process, interactions were observed between algin inclusions and the co-products mixture ratios. Higher algin inclusions increase the values for hardness, resilience, cohesiveness, chewiness, and adhesiveness of pet treats. Algin contains gelling abilities, which created more stable, restructured pet treats. As for implications, the use of the right amounts of each co-product could lead to better quality products, better consumer acceptance, and could reduce production costs. Also, hydrocolloids may allow difficult to process products, such as liver, to be incorporated into more product mixes. I would like to thank the following institutions for the support of this research: Auburn University, Alabama Agricultural Experiment Station, USDA NIFA, Balkan Corp., Auburn University Poultry Science Department, the Starkey Lab members, Drs. Murray and Dr. Garner. That is the conclusion of my presentation. I want to thank you for your attention and would now be happy to address any questions you may have.